Hello everyone, section 4.3, rotations. So this first one that we're going to do involves using a protractor, and the only protractor I have with me right now is the one on the end of my compass. It's not perfect, it's not what I recommend using, it's what I have with me. So first thing we need to do is we need to connect A to our center of rotation, point P, and then we're going to set our protractor up so that we can measure 60 degrees. So we set the center of our protractor on point P, the edge along the line that connects out to point A, and then we mark 60 degrees. And now I'm going to extend out past that mark. Get it more accurate. There we go. And somewhere along this ray here is point A prime. Okay. How far away is it? Well, I'm actually going to use the compass for this, just to set my distance to the length of where point A is. Now I've got the radius set for A. I can come out here, and there is A prime. Alright, I'm going to do the same thing for, let's do C next. Connect from P to C. Set my protractor up again. Mark 60 degrees. Draw my line from P through that mark. And set my radius to a length equal to where C is. And intersect. There is C prime. One more time for B. Connect P to B. Set my protractor up. Mark 60 degrees. Draw my ray. Set my radius to the length B. And draw my arc. There is B prime. And I can finish off the drawing. Connecting. A prime, B prime, C prime. And that is a 60-degree rotation. Notice that I rotated counterclockwise. By definition, all of our rotations are going to be counterclockwise. So A went 60 degrees, C went 60 degrees, B went 60 degrees. This figure is congruent to the original figure, and it's the same distance away from point P, the center of rotation, as the original figure. Okay. Example 2. We're going to graph triangle ABC, these coordinates, and we're going to rotate it 180 degrees. So start by graphing them. A is at 3, 1. A. B is at 3, 4. B, and C is at 1, 1. Here's point C. Quick sketch. There's triangle ABC. Now, without using the rules, I can actually physically turn the paper 180 degrees. And imagining now that this is quadrant 1, quadrant 2, quadrant 3, quadrant 4. This is my new C prime, A prime, B prime. A prime is at -3, -1. B prime is at -3, -4. And C prime is at -1, -1. So when I go back to the original orientation, like this, I can plot these. There's C, there's A, there's B prime, B prime, A prime, C prime. Connect them. And here is my image, triangle A prime, B prime, C prime. Using the rules down here, if I'm doing a 180-degree rotation, you just negate the coordinates of each of the points. So A prime will be -3, -1, B prime will be -3, -4, C prime will be -1, -1, which is exactly what we have plotted here. Okay, example 3. Given regular pentagon, penta, with a center point X, name the image of point E for a 72-degree rotation about point X. 72 degrees may sound like a random number, but it is not. If I draw in the central angle here, EXP, there are 5 of these central angles as we go around this pentagon. They're all congruent because it is a regular pentagon, meaning all the sides are the same, all the angles are the same. So this angle is the same as the other 4 angles. All 5 of them add up to 360 degrees. 360 divided by 5 is 72 degrees. So this rotation angle is not random. Okay? So if we start point E and we rotate it 72 degrees counterclockwise, because by definition all our rotations are going to be counterclockwise, it ends up at point P. If I start at point P and I go 216 degrees, again not random, it's a multiple of 72. So if I go 216 degrees, 72, 144, 216 degrees, end up at point N. If I start at point T, I go 144 degrees, 72, 144, I end up at point E. Okay. Example 4. Graph segment RS with endpoints R and S and its image after composition. So we're going to do a rotation of 180 degrees about the origin, and then we're going to do a reflection in the y-axis. So let's start off by plotting 1, -3. There's point R. And 2, -6. 2, -6. R. Point S. Segment RS. Okay. If we do a 180-degree rotation, we can do the turning of the paper and read the new coordinates. -1, +3, -2, +6. Or we can use the rule, which is to negate the coordinates. -1, +3, -2, +6. And we're plotting R prime, -1, +3, R prime, -2, +6, S prime, and connecting them. So we have R prime, S prime, segment R prime, S prime. Now, we're going to do a reflection in the y-axis. So R double prime ends up one space to the right of the y-axis, since R prime is one space to the left. S prime is going to end up two spaces to the right of the y-axis. S double prime. And we connect them. Again, we can use the rule for reflection in the y-axis, which is to negate the x-coordinate. So after the rotation, R prime was -1, +3, and S prime was -2, +6. And a reflection in the y-axis negates the x-coordinates. R double prime is 1, 3. S double prime is 2, 6, which is exactly what we plotted. Example 5. Does the figure have rotational symmetry? If so, describe any rotations that map the figure onto itself. So, does this equilateral triangle have any rotational symmetry? Yes. So now the question is, what is the angle of rotation? So, it has lines of reflectional symmetry here, here, and here. Which means right here is a center of rotation. Okay, so that's our center of rotation. If we rotate from here to here, how many degrees have we gone? Well, we've gone through this arc, which is this angle, which is a central angle for this equilateral triangle. There are 3 of these central angles. 360 degrees divided by 3 is equal to 120. So yes, we rotate 120 degrees for rotational symmetry. Okay? It does not have point symmetry, because if I rotate it 180 degrees, it doesn't look the way it did originally. It is upside down. It's pointed the wrong way. So it does not have rotational symmetry. It has point symmetry. It only has rotational symmetry of 180 degrees. Part B. Scalene triangle does not have any rotational symmetry. No. And as we rotate it around, it will never look the way it did when we had it in its original orientation. It has no rotational symmetry. Part C. Part C, the way it looks right now, I've got a corner cut off in the bottom left, I've got a corner cut off in the bottom right. If I rotate it this much, top left, bottom right, corners are cut off, doesn't look the same. Suddenly when I get to here, corners cut off in the bottom left, corners cut off on the bottom right, I have rotated it exactly 180 degrees, and it looks the way it did before. So yes, it has rotational symmetry of exactly 180 degrees, which means that the rotational symmetry can be simplified to be calling it point symmetry. Point symmetry means rotational symmetry of exactly 180 degrees. Thank you very much.